Dear students, continuing with our lecture series on named reactions, this is our 28th lecture, and continuing with our previous lecture where we have studied about Baylis-Hillman reaction. Now, in this lecture, we will see how optically active products they can be formed through Baylis-Hillman reaction. So, Baylis-Hillman reaction where asymmetric products they are formed, optically active products they are formed. Anisotropy Baylis-Hillman reaction is known as asymmetric Baylis-Hillman reaction. So as we have seen in the previous lecture that Baylis-Hillman reaction is basically hydroxy alkylation of the activated alkenes. Activated alkenes means alkenes having lactone withdrawing group. And here a new carbon-carbon bond is formed between this carbon and this carbon of the either carbon oxygen double bonded compounds or carbon nitrogen double bonded compounds. And for example, methyl acrylate on reaction with ketones in presence of triethylamine as catalyst will give us alpha hydroxy alkenes as the product. And I have told you the mechanism that in the first step the trialkylamines they will attack this lactophilic carbon due to the presence of this carbonyl compound, and we will get these types of enolate which are resonance hybrid of these two structures, and these enolates they will act as nucleophiles to attack this lactophilic carbon of the carbonyl compounds to give us these types of oxygen negative compounds which will take up the proton from the alpha carbon to this uh, compound, and with the elimination of the catalyst we will get alpha hydroxyalkenes as the product. Now when we are talking about asymmetric Baylis-Hillman reaction, then different types of routes they can be used. That is, either we can use chiral auxiliary compounds as catalyst, or we can use chiral Lewis base as catalyst, chiral Lewis acid as catalyst, or chiral Brønsted acids as co-catalyst for formation of asymmetric products in case of Baylis-Hillman reaction. So, for example, first type of asymmetric Baylis-Hillman reaction is where we use chiral auxiliary. For example, if we are using substituted uploser sultan, when this is reacted with aldehydes, this uploser sultan is a chiral auxiliary, and this can lead to the formation of asymmetric products. So when this uploser sultam is reacted with aldehydes in presence of DAPCO as catalyst in dichloromethane as solvent, these will be converting this part will react with the aldehyde. This will act as the alkene part, this will act as the carbonyl part in the MBH reaction. So basically reaction will take place in this carbon-carbon double bond and this carbon-oxygen double bond, and we will get optically pure 1,3-dioxane 4-ons as the intermediates. And these intermediates on reaction with camphor sulfonic acid in methanol will give us these types of asymmetric MBH attacks. So these optically pure 1,3-dioxane 4-ons they will be converted into these types of alpha hydroxy alkenes as the product, which are anisotropy. So only one if only one product, an selective product is formed, we say that the reaction is asymmetric Morita-Baylis-Hillman reaction. Similarly, another example of chiral auxiliaries using these types of chiral allenes and even chiral amines they can also be used. So these chiral allenes, when they react with these types of shift spaces, they undergo the formation of a new carbon-carbon bond between these allenes and this carbon-nitrogen double bonded shift base. So this carbon from here and this carbon from this shift base, they will form a new carbon-carbon bond, and we will get a diastereoselective product formation. These types of asymmetric reactions. Then second type of asymmetric MBH reaction can take place when we use chiral Lewis base as the catalyst. And most common among these is chiral tertiamine catalyst, which are used for anisoselective MBH reactions. And most common among these is Syncona alkaloids derivatives. So beta ICD, this molecule where this oxygen is alpha, this enantiomer is called as beta ICD. This is an natural alkali derivative. When this is used as catalyst, so these types of alpha beta unsaturated ketone, they react with aldehydes in presence of DMF as solvent, and they will undergo this type of asymmetric MBH adaptation. So this 111,333 hexafluoroisopropyl acrylate, this substrate, when reacted with aldehydes in presence of beta ICD, they will give us asymmetric MBH products through this reaction. Then another chiral Lewis base catalyst is chiral phosphine squaramide molecules. So this is a squaramide molecule. So when these types of chiral phosphine squaramide molecules, they act as catalyst, and they undergo an intramolecular asymmetric MBH reaction, where this part of the molecule will act as the carbonyl component, and this part of the molecule will act as alkene, and this will undergo cyclization at this place with the hydroalkylation at the carbonyl, and we can see that we will get an rich cyclic product at room temperature. And the products, they depending upon this are different type of substituent we can have. The yield of the products formed can range from 64 to 98%, whereas isomeric excess of the product formed ranges from 88 to 93%. Then chiral Lewis acid based catalyst, few more examples. When cyclopentanone react with aldehydes with this type of catalyst, whose planar chiral DMP catalyst, this is known as, this is ferrocene part, and all the hydrogens of this one cyclopentadiene, they are replaced by phenyl groups. So this is called as fuse planar chiral DMAP catalyst. This part is DMAP. So this act as an asymmetric chiral catalyst in the presence of magnesium iodide. This will give us asymmetric MBH products. And here the MgI2 will act as a co-catalyst because this is a Lewis acid. Then even simple diamines like these chiral pyrrolidine, they can also act as catalyst for the synthesis of asymmetric MBH products. Then another type of catalyst which is chiral Lewis base catalyst is these types of chiral phosphine MBH catalysts. So they contain a Lewis base and a Brønsted acid. and they can lead to the formation of asymmetric products in case of uh, Morita Baylis-Hillman reaction. And here also the yield of the products ranges from 86 to 96%, whereas enantiomeric excess of the products formed is ranges from 79 to 92%. Then third category is chiral Lewis acid catalysts. So these types of Lewis acids, they can act as catalyst for asymmetric Baylis-Hillman reactions, which involve aldehydes and alpha beta unsaturated ketones, where unsaturation is due to carbon carbon triple bond. And these in presence of trimethyl silyl iodide and chiral catalyst boron based. These types of catalysts, they convert these reactants into selective product formation through MBH reactions. Then we can also use chiral palladium Panzer complexes like this. Here also these are chiral catalysts which can be used for MBH reaction in case of carbon nitrogen double bonds. So this part will act as the substitution for carbonyl. This will act as alkene and hydroalkylation at this carbon and this carbon. A new carbon-carbon bond will be formed, and hydro ASA MBH products, they will be formed, but the product formed, they will be asymmetric in nature. And here also the selectivity or enantiomeric excess of the products formed can range from 76 to 98%, depending upon the value of this R. Then chiral Brønsted acid, using this as co-catalyst in addition to some base. For example, Jacobson's thiourea catalyst. This is called as Jacobson's thiourea catalyst. This part is thiourea, and these substitutions, they can lead to the formation of a chiral catalyst, and this chiral catalyst can lead to the formation of chiral products through ASA-MBH reaction. So when these types of carbon nitrogen double bonded compounds, they react with activated alkenes, we will get selective ASA-MBH products. Then these types of bifunctional catalysts, which are chiral in nature, based on thiourea and phenyl phosphines, they can also act as catalyst for asymmetric MBH reaction. So when acrylates, they react with aromatic aldehyde in presence of these phosphine thiourea based catalysts, which are chiral in nature, they will lead to the formation of enantiomeric MBH products, where enantiomeric excess of the products ranges from 9 to 77%. So these reactions are also very important for the synthesis of selective or asymmetric products. Then another example of these types of reaction is when we use proline derivatives as co-catalyst in addition to the base. So DEPCO will act as the base, and these will act as chiral catalyst or co-catalyst. When these are reacted in presence of these types of substituted alpha beta unsaturated aldehydes and alpha amidosulfones, they will give us these types of ASA-MBH reactions, where we will get selective products, and selectivity of these product formation, that is E to Z ratio, ranges from 10 to 1, that is E product is formed 10 times to Z form, and this ranges from 10 to 1 to 19 to 1 depending upon the values for this R and R1. Similarly, anisometric excess of the products formed will range from 82 to 99%. So the products formed, they are highly anisoselective. So these are the references which have been consulted for preparing this lecture. Thank you very much.